Hi, welcome to this particular module. Now, in this module we will see a circuit that is known as automatic gain controller, is also called automatic volume controller. So, as the name suggests, automatic volume controller. So, what does it mean? That if a person is speaking, right, and suddenly his voice is too high, that should not affect tremendously to our loudspeaker, right, it should not like burst, correct. So, how can you control that change in input signal? We want to have a constant output signal, right. Or let us take another example where you have a sensor and you know that for a particular range of input signal your output should be x value, and if there is a change in input signal which is not required, is unwanted change in input signal, we do not want our output to be distorted or output to get changed, because that output is connected to further electronic modules. So, in that how can we make sure that even there is a random change in input signal which is undesired, the output should not get affected, alright. So, for this kind of application we can use automatic gain controller. So, if you see the slide shows that like I said, we require the gain of the amplifier to be adjustable since the input keeps varying. The output of sensor can vary depending on the strength of input signal, that we know, right, and the amplifier's gain can be adjustable when the input signal has a narrow bandwidth, and the control system is called automatic gain controller AGC. Or since we may wish to maintain the output voltage amplifier at constant level, we also can call it as a voltage automatic volume controller. Now, if you see this circuit, right. So, first let us see a plot. Here what you see, until this VPI the output almost changes linearly, right, and above VPI if there is an, and then we reach this particular point where your output is kind of constant, right. So, how to get this constant, even there is change in VPI signal, as you can see here, if we change its signal is there, we are not looking at the change in the output, right. How can we obtain this constant output? So, for that what we need to do, we need to use this circuit, and in this circuit there is a reference voltage, the input voltage is a sine wave, and sine wave is further multiplied by once again multiplied becoming sine square, right. So, when you have a sine square it is like a ripples, or you can say a full wave rectifier kind of signal, and since there is a integrator right over here, if you can see R and C forms an integrator, what the output will be almost a constant, right. That is what we see here, and the output is constant, alright. So, using this circuit we can control the output voltage. Again there is a feedback signal. So, if there is an error, that error signal goes here, and then we can compare it with this input voltage, right, which is further rectified, and further the error is subtracted to make sure that output voltage remains constant. So, the signal that is obtained here is always compared with the reference voltage which is given over here. Okay. So, in terms of operation it is very simple, and the output of the system remains constant at under root of 2 VR Vref. We will see how we can get this particular equation or a formula and after a certain input voltage. That means that output voltage will be constant at this particular point, and the typical input output characteristics is shown here in the figure, where you see a Vi versus Vo, or we can say Vpi versus Vpo. So, let us see how we can implement this particular circuit using a TI board, and we will see the output voltage also, how the output voltage changes with respect to input, and we will see that even there is unwanted change in input signal, the output voltage remains constant. Okay. So, let us see this. I will ask Anil to show us the implementation of the circuit on the TI board.
We will be doing the experiment on the board for the automatic gain controller circuit, which you have just seen in theory. So, just quickly recap, doing a recap. What is the automatic gain control? This circuit is mainly used. So, as you can see on the screen, this is the circuit that we will be trying out on the board today. So, what basically means, what does this automatic gain control? Automatic gain control is also called, as you would be aware now, it is also called automatic volume control. So, AGC or AVC. What it does is basically whatever, so so input voltage, like especially in real world practical applications, input voltage might be having a particular pattern, but occasionally there might be fluctuations like this. So, for these fluctuations you do not want the output to go follow the input in these fluctuations, and you want the output to be having a defined gain, and its gain needs to be controlled to set values no matter how the input changes. So, this is the essence of automatic gain control that you have studied. So, so let us we will not go into the full details of this because that is already covered. So, in the circuit what we are trying to do today, that only we will see right now. So, what we have, the circuit, we have 2 multipliers here and a amplifier, op amp based amplifier. So, what happens is basically this is your input voltage, okay, and so let us say you apply an input voltage of V sin omega t as the V in. So, you want your V in, if your V fluctuates, even if your V fluctuates, your output should be the amplitude of your output should be reasonably constant, let us say Vc, okay. So, this is your fundamental aim of designing the circuit. So, what happens in these blocks are, so V in has one component of there are 2 multipliers, this and this multiplier has one input as a feedback from the output, okay. So, what then the next multiplier is there, what this next multiplier does is, it is like a multiplication operation, and let's say after the multiplication, so this input has a measure of the amplitude of the output, that is Vc, and so here the output of the multiplier will be V in into Vc sin omega t by A, where A is the amplification factor of the multiplier, okay. So, this is the output at this point 1. Now, at 2 what happens is this same signal is multiplied again with itself. So, what happens is you will get some voltage which is V in Vc by A whole square into sin square omega t at here 2. So, this is 2, okay. So, this is like a diode based rectification operation. So, sin square omega t would have information like this, and you can get the what is the amplitude of, it has information about the amplitude of the output as also the amplitude of the input, correct. So, then it goes to an op amp based amplifier section. So, this amplifier acts as an integrator here, okay, acts as an integrator, and what it does is it tries to see how much the output voltage is fluctuating from this reference voltage, and it will give you an error voltage, and that error voltage, so the accumulation will be there in the output, and that gets fed back to the multiplier section, as a result of which whatever be the fluctuation of the input, the output voltage remains same. So, to put it simply, let us say here your output is V in into Vc by A sin omega t, and let us say your output is proportional to this. If your V in goes down, your Vc has to go up to maintain this output voltage constant, let us say, or if your V in goes up, your Vc has to go down to retain your output voltage constant. So, that is what the whole circuit does. This is the essence, and the theory has already been covered. So, now in the experiment what we will do is, we will have this, we have connected this circuit on the board, and then we will apply a sine wave and show you what is the output and how the output is changing, okay. So, now so this is the whole circuit. We have 2 multipliers and then an op amp section, and as a result of which, with the changes in input voltage, with even minor changes in the input voltage amplitude, the output voltage remains reasonably constant. So, now let us see the board. So here we have the circuit. So as we have seen in previous sessions, we have the multiplier section here. Okay, since we have to use two multipliers, so we have used two multiplier sections, this and this, and then we had to use a op amp section. So we have used the op amp section also here. So we have used this op amp section. Okay, so the input voltage is applied from the function generator. Okay, at a sine wave of let us say 50 kilohertz is applied, and its voltages are and its amplitude can be changed, and the connections are made accordingly for the multiplier. So as we did before also, the multiplier has x1, x2, y1, y2, z1, z2 inputs. The x2, y2 and z2 inputs of the multipliers, both multipliers are grounded, and the input, first input is applied to x1. So this yellow wire here is x1, which is your input from your function generator, and you have your y1. Okay, this y1 is this green wire. Y1 is coming from where? Y1 is coming from this op amp here. So that is the feedback which we saw, that is coming from the output of the op amp, this green wire which we are holding up here. So this green wire is there. So this one, the first multiplier which we saw, that connection, the output of that multiplier, as we have seen before, has to be fed back for the negative feedback to work for the multiplier. So that is this wire, this blue wire here, this blue wire here. The output of the multiplier is fed back to the Z1 input that goes to the negative terminal of the multiplier op amp. Okay, then the output of this multiplier again goes as the input, one of the inputs, through this wire. You can see this wire, right? So it again goes as the input to the next multiplier section here, x1. Again x2 is grounded like this, then x2 is grounded, as so is y2, and y1 what we will have, y1, because the second multiplier has the same signal, right? We had seen we use the same signal at both the input terminals of the second multiplier. So that is what this brown wire does, this brown wire which I am holding up, which we are showing with the pen here. So this brown wire shorts or connects the same output of the previous multiplier as the input, both the inputs of the second multiplier, and as usual the Z2 terminal is grounded and Z1 is fed back from the output through this long brown wire, this wire which I am holding. The output is fed back as well to the x2 terminal, to the x1 terminal through this green wire. The output is fed back through this green wire, not the brown wire. The brown wire is basically ground for the probes. This is the green wire, and then what has to happen, the output from the second multiplier through this gray wire here has to go to the resistor network, which is shown in this small breadboard. We saw two resistors, right? One resistor goes through a capacitor to the output terminal of the op amp, and another resistor comes in through the reference voltage which we apply. The concepts of the reference voltage etc. have been discussed to you, and so this one resistor comes in through the reference voltage, and the capacitor goes to the output of the op amp, and again the inputs of the op amp are those, and the positive terminal of the op amp is grounded through this blue wire, and the negative terminal is connected to the other end of the resistor pair, these two resistors, and the capacitor connects across the output and the negative terminal of the op amp here. So this is the output. So this is the whole connection of the circuit. Okay, and the output of the op amp finally, as we have seen before, again goes back all the way back to the input of the first multiplier. So this completes the circuit. So now what will happen? So we will give input to the first multiplier's input through this yellow wire, and we will see the output from where? We will see the output from the red wire, and we will see the red wire is actually giving the supply for the reference voltage here, this red wire, and this white wire here is where we will see the output, which is the output of the op amp. It is connected there itself because it is connected to the other end of the capacitor, correct? So now let us see the function generator first. On our right, yes. So, in the function generator you can see we are applying 50 kilohertz sine wave at 5 volt peak to peak, at 5 volt peak to peak, sine wave 50 kilohertz at 5 volt peak to peak. Okay. Now, let us see the output voltage in the oscilloscope. So, we have shown the output voltage, output signal and the input signal. So, let us see the oscilloscope. Yes, now you can see the oscilloscope. So, the blue is the input signal and the yellow is the gain controlled output. So, we have adjusted the scales now so that you can see the output and the input on the same reference level. So, let us see, we had kept the input voltage at 5 volt peak to peak. So, let us just increase the voltage ranges, and you will see that even when the input voltage is going from a 5 volt peak to peak swing to 10 volt peak to peak swing, you will still see that the output voltage is reasonably constant, which is what we want in an automatic gain controlled or automatic volume controlled environment. So, let us just increase the input voltage now. So, so through the function generator I will be increasing the input voltage, but just focus on the oscilloscope to see how the output is changing. So, we are just seeing the circuit again, yeah. So, we are seeing the oscilloscope again. So, this is now 6 volt, earlier it was 5 volt. So, still if you see the output voltage is constant, it is a sinusoid of a reasonably low amplitude, because that is what we have designed for. So, this is 6 volt peak to peak, still the output voltage you can see that it is remaining constant. This is 7 volt peak to peak, 8 volt peak to peak, 9 volt peak to peak, 10 volt peak to peak. Still you can see that the output voltage is reasonably remaining constant. If you go beyond this, what happens is that if let us say you cross 10 volt peak to peak or 12 volt peak to peak, we have used 3 sections of circuits in the circuit, right. We have 2 levels of multipliers and an op amp. In one of these circuits, in many of the intermediate stages, they can reach saturation levels, because of which your output voltage need not necessarily follow the input. But you can see very clearly that when we swing from 5 volt to 10 volt peak to peak, which is a very huge swing, your output voltage is remaining constant. So, which is the yellow, this is the automatic gain control operation which we have demonstrated through this experiment. Thank you.